So at this point, we've covered a number of different hypothesis tests, and typically we just jump to the calculator when it comes to a hypothesis test problem, and we let the calculator do the math for us. There is a lot of math going on in the background, and on multiple choice problems, occasionally you'll see the equations with everything plugged in. So each of these tests has different types of standard deviations, different types of equations. So in this video, we're just going to refresh on what's actually happening as far as the math that's going on in the background of that calculator. To start, we're going to go over the standard deviations for the different types of tests. And if you ever encounter an FRQ where it asks you to explain or interpret a standard deviation, you want to word it similar to this up here, where you're saying the standard deviation is telling us how far away from the mean the data is on average. So we're looking at the entire distribution, all of the points collectively, and we're saying how far away are these points from the mean on average. And of course, just like everything else, we want to put our answer in the context of the problem. So there's two types of problems that we deal with, primarily at least, categorical and quantitative problems. Categorical problems give us a proportion. We're asked a question that's non-numerical, so maybe it's the percentage of people who have blue eyes, maybe it's the proportion of people who's responded yes to a question. So we boil that down to just a percentage, and then we can use that percentage to find a standard deviation, radical PQ over N. If we're doing a confidence interval, we use the results of the sample. If we're doing a hypothesis test, we're going to use whatever value our null hypothesis says. So we might have a null hypothesis of 0.5. In our problem, maybe our p hat, our sample result, is 0.6. Make sure you're putting this value into that standard deviation. Quantitative, we use S over radical N. S is the standard deviation of the sample. Okay. If it were the standard deviation of the whole population, it would be labeled with sigma. And if we knew what sigma was, we could use a z-score. All right. In the real world, we pretty much never know what sigma is. We don't know the standard deviation of the whole population. If we did, we probably wouldn't be doing a hypothesis test or a confidence interval, because we would probably also know what the true mean of the population was. So S over radical N, it's the same for both confidence intervals and hypothesis tests. So that was the standard deviation. Let's move on to the actual test statistic. When we're talking about a test statistic, we're talking about a z-score, a t-score, or a chi-square value. And this is being calculated for a sample result, and it's based on a model that's formed around our null hypothesis. It's going to tell us how unusual our test result was, our sample result, under the assumption that the null hypothesis is true. The equations for single sample inference are nice and simple. Basically, we're just going to take our sample result, we're going to subtract the null hypothesis value, and we're going to divide it by the standard deviation. So for categorical data, again, we're dealing with proportions. Categorical data and proportion problems are always z-scores. Quantitative, once we have x bars, we're working with t-scores. Our null hypothesis always comes second here. All right, so that's always being subtracted from the sample result. So the p hat is the sample, the x bar is the sample. This is the hypothesis true mean of the population, or true proportion of the population over here. Okay, and we divide by that standard deviation, and that's the same standard deviation that we had on the previous slide. So PQ over N. Again, that P is from the null hypothesis value, not from that sample P hat. Okay, and S over radical N, it's the same for confidence intervals as it is for hypothesis tests. Okay, for a confidence interval for this one, we would change that to P hat and Q hat, because there is no null hypothesis. So for example, is it unusual to flip a coin 30 times and get more than 30 heads? We always start with our hypotheses. Okay, if it's a fair coin, we're going to get heads 50% of the time. If it's not fair, we would get it some other percentage. Okay, the true proportion of heads is some other proportion. All right, so this is categorical data. Either it comes up heads or it comes up tails. All right, this is giving us our sample result. That's our p hat, 20 out of 30. Plug everything in. Make sure when you find your standard deviation, use that null hypothesis value and not the p hat value. So we get a z-score of 1.82, and from that we can say we could use it to find a p-value, or just from that z-score we know that this is not an unusual result because it's not more than 2 standard deviations from the mean. Okay, it's going to give us a p-value over that 5% alpha level. Two sample inference equations are more complicated. So let's start off with null hypotheses. If we have two samples, let's say it's categorical data, we would start off with a null hypothesis, and the null hypothesis always says the same thing. It says that our two population parameters, proportion 1 and proportion 2, are equal. Our alternative, in this case, I have it saying that they're not equal to, but it could be less than, it could be greater than. If this was a quantitative data problem, it would be the same thing. We would just have mu1, mu2. Okay, our hypotheses are always about population parameters, meaning it's always about p or mu. It's never about p hat or x bar because those are samples. They don't go in our hypotheses. So when we actually find these test statistics, we're always saying, okay, is the difference between our two samples unusual? Okay, this is just coming from our null hypothesis the same way as it did in the other one. And it's always 0, so in most cases we just leave it off. Okay, so is that difference large based on a standard deviation? Okay, which we haven't found yet. So two separate samples, each with their own standard deviation, we're going to need to combine them. Okay, let's deal with the quantitative one first. So here's our two samples. Right, first standard deviation, second standard deviation. We're not allowed to do this and just add them. Okay, common mistake. Okay, we can't just add standard deviations. Instead, we have to add their variances. And that's going to give us the variance of our combined two distributions. Okay, so we take this whole thing, we square it. Okay, you can see that here. Same thing with the other one. Okay, we're going to add those two together. That gives us a variance, and to turn it back into a standard deviation, we square root it. Okay, when we distribute that square there, it cancels out that square root on the bottom. So we end up with just s squared over n plus s squared over n for each of those respective samples. Okay, that's going to be the standard deviation that goes underneath the difference between those two sample results. Okay, and we want to see, is that unusually large? Do we get a t-score that's more than 2 away? T-scores don't match up with z-scores exactly, but they're pretty close, where once we pass 2, that's usually signifying an unusual result. Just like z-scores, we can go to our calculator, we can go to t-CDF or normal CDF once we get this test statistic, okay, and the value that that's equal to get an actual probability, a p-value. So for the categorical one, this is the particular tricky one, right? Because for two proportion hypothesis tests and two proportion hypothesis tests only, we're going to pool our two samples. We're going to create one large p-hat. And that's based on the fact that up here, okay, our null hypothesis is saying that our two proportions are actually the same. Okay, any difference that we're seeing in these two sample results is just a result of natural sampling variation. They're actually the same thing. If we were to go out and survey everybody, do a full census, we would see that those are actually the same. So to get a better idea, we're going to pool our two values and make a single p-hat, all right, and use that on the top of both of these fractions. Okay, so we take all of our successes, we add them together, we take both samples, we add them together, we make one sample combined of the two of them. That's our p-hat, pooled, okay? We have the corresponding q-hat, and we put both of those on top of both these fractions over their corresponding sample sizes. All right, when it comes to multiple choice problems, you'll probably see them written out like this. It won't actually give you the numbers that they're equal to. It's just going to have all those equations filled in with numbers. Some of them will be different. Okay, if this was a confidence interval, we wouldn't pool. We would keep both of these standard deviations separate like that. For linear regression problems, we're simply going to divide the point estimate by the standard deviation. Let's say we have this example looking at the relationship between blood sugar levels and brain shrinkage. Normally our table would have a lot of additional information here, but this is the important information. So here's our slope. Okay, this is the point estimate for the slope. Point estimate is just whatever our sample results showed. And then this is the standard error of that slope. Okay, up here is the y-intercept. So our null hypothesis would be that beta equals 0. That's saying that there is no association between these two variables. If we make a scatter plot, it's just going to look like just completely scattered, and there's no actual like linear association there. Alternative is saying that it's not equal to 0, so there is some kind of association. We are going to take our point estimate, that's our B1 here. Okay, we're going to subtract our null hypothesis value just like we did with a one sample inference. Okay, so we're subtracting 0, and we're always subtracting 0. So again, we can just leave that off. And then we divide it by the standard deviation. So this is really similar to one sample problems. Okay, we're going to take this 1.6. Okay, we subtract the 0. We can just leave that off. And we divide by that standard error. Okay, and that'll give us that test statistic. The last type are chi-squared problems. Remember when we write our hypotheses for chi-square problems, they're always written down as words, okay? We don't have like p equals something or mu equals something, all right? We don't have to center our distribution around some value like we do with proportion problems and mean problems. Like in the coin problem where we had our null hypothesis was 0.5, okay, 0.5 would go in the middle of our curve. For the two sample problems where we're starting off saying that there's no difference between these two, we would put 0 in the middle of our normal curve, okay? And we're going to see like how unusual is any difference that we get. With chi-square distributions, they're always starting at 0, and it goes to the right, and it's right-tailed, okay? So it's not like we're putting something in the center like we are with those other two. It's just always 0 over here. We're going to get some value for our chi-square test statistic, okay? And remember, that's going to be observed minus expected squared over expected. Okay, we add them all up. All right, and these tests are always right-tailed. So we just take that, we go out to the right. The only thing we need to know is this chi-square value and degrees of freedom. To close out the video, let's do two example problems here. So in this one, we have a blogger that claims adults in the US on average drink 5 8-ounce glasses of water per day. There's some researchers, they're skeptical. They take a sample of 24 adults. Okay, they summarize the information down here. We can see n equals 24. That's our sample size. This was the mean. Okay, it's the mean of a sample, so it's an X bar. That's the standard deviation of our sample. It gives us some extra stuff here. If we write out our hypotheses, mu would equal 5. That would be our null hypothesis. We want to see if this is correct or incorrect, so not equal to 5 is our alternative. First step is figuring out what type of test this is. We have one sample. It's a sample. So there's one sample, and this is quantitative. Okay, if we found the mean and a standard deviation, we know it's quantitative. Otherwise, they would be giving us a percentage of something, which would tell us that it's categorical, right? Don't mix this up with a percentage as like a p-hat or a p, because that's just the alpha level. So this is a one sample t-test. We're going to use a t-score for this. We're always taking our sample result, our point estimate. We're comparing it to our null hypothesis value, and we're saying, is that surprisingly different based on some standard deviation down on the bottom here? We plug everything in. This is likely what the answer would look like on a multiple choice problem, but we could calculate it out. And it's going to do a whole bunch of things here, like it's going to switch these two as one of the answers. It's going to change the bottom here. If you actually calculate this out, you're going to see that it equals this, the standard deviation of the mean. So you'll see a bunch of different options. And in this last example, we have a study examining whether males and females in the 19 to 25 age group are equally likely to live with their parents. So we have a sample of males, a sample of females. Okay, it's telling us how many of each lived with their parents. Right, this is a categorical question. The question being asked is, do you live with your parents, yes or no? All right, our null hypothesis is always saying that these two proportions are the same. There's no difference here. Our alternative, in this case, we want to see, is there a difference? This is going to be a two proportion z-test. So we have two different samples, their proportions. Okay. Anytime we're dealing with proportions, it's a z-score. All right, and this whole video is about hypothesis tests. But all right, so for a hypothesis test, we're going to have to pool this data. So we take all of the people that live with their parents, we add them together. We take both samples, we add them together. Okay, we get a pooled p-hat. So what this is based on is our null hypothesis. So if the null hypothesis is true, and our whole test is based on an assumption that the null hypothesis is true. Okay, any difference that we see in our samples, okay, and we do see a difference here. So 43.8% for males, 35.1% for females, is just a result of natural sampling variation. If we went out and we talked to all the males in that age group, all the females in the age group, we'd find out that they actually would live with their parents at the same rate. So if that's true, the best thing for us to do is just to take all of our data, put it together, and come up with a single value to represent both of these samples collectively. So this is the value that goes into our standard deviation here. It's going to go into our pooled p-hat down on the bottom here, and then 1 minus that for the pooled q-hat. Okay, is the difference between these two proportions large considering or compared to a standard deviation that's built around an assumption that the two proportions are actually the same? Okay, and we'll find that it is, because that's a really big z-score. Just one other note here, sometimes they'll take both of these numerators and they'll factor them out and they'll put it out front. Okay, so if you see something like this, okay, they might change the bottom, where if we distribute that in, it would turn into that. So just don't get confused if you see it written like that instead.